In this lesson, we will be discussing chemical separations. And chemical separations are some of the most important parts of chemistry. As a chemist, you will find that it's very useful to be able to separate chemicals for two main reasons. The first is what we call purification, and that's the process of taking a mixture of chemicals where one of them is more useful than the rest and removing all those other materials. An example of this would be if you worked in a pharmaceutical company. If you're responsible for producing a drug, you want to make sure that that drug contains only that drug and not any of the byproducts or starting materials or solvents that may remain from the process of producing that drug. Now, the second reason why chemical separations are so useful is for analysis. In the last course, we learned about spectroscopy, and we saw that different types of molecules can be identified or differentiated based upon their spectroscopic properties. So we saw that an IR spectrum or an NMR spectrum can be used to identify chemicals. However, we also saw that if we are looking at a mixture of chemicals, that spectrum will actually consist of a combination of all of the different chemicals that are present in that mixture. And this can make it very difficult to do a comparison of one compound with a known set of spectroscopic data. So, for this reason, being able to perform a chemical separation is very useful because we can take a complex mixture and break it down into its principal components and then measure spectroscopic data. Now, separating chemicals is much more complicated than separating ordinary household items. Now, you may be accustomed to sorting things like coins or socks or pretty much anything that can be divided up into separate categories. But with chemicals, we don't have the same ability where we can physically pick up the chemical and move it to one side of a flask and then move a chemical from a different category to the other side of a flask. We just cannot manipulate chemicals in that way. For that reason, separations of chemicals must be based on a difference in their physical properties. In other words, we're looking at the bulk behavior of a large amount of chemical and hoping that it can be differentiated from the bulk behavior of another chemical which may constitute the impurity. Now, one property that is frequently exploited is the solubility of chemicals. So let's say we have a flask that contains a mixture of two chemicals, as indicated by the light circles and the dark circles. And let's say that the chemicals represented by the dark circles are ionic in nature. That means highly polar and very water soluble. And let's say that the light colored circles represent a nonpolar compound, which is not going to be soluble in water. If we expose that mixture of chemicals to water, we would expect to see the ionic compound dissolve in the liquid water, as indicated by the darkening of the solution. However, the nonpolar compound would not dissolve. In fact, it should just remain at the bottom of the flask or float depending upon its density. And if we were to filter that off, we would be able to remove that liquid from the solid material. Now, the liquid that remains after the filtration can then be evaporated. And once the water is removed, we can separate out or just crystallize out those dark circles which indicate the ionic compound. Now, another property that is commonly exploited in separating chemicals is the boiling point or the volatility of a compound. Let's say we were to start off with a flask just containing water and sodium chloride, so simple brine, saline. If we wanted to remove the water from the sodium chloride, all we would have to do is heat up that water. Now, what we would expect to happen is for the water vapors to escape the flask, and then over time we would be left with just the sodium chloride. Why? Because the sodium chloride is not volatile. It will not boil at a typical or a normal temperature. However, the water will. But let's say we have the same situation, but we want to collect the water for some reason. Well, all we have to do is attach some kind of a apparatus or device that would collect those water vapors as they escape, and then recondense them down into a liquid, maybe by using some kind of a cooling bath. And then that liquid water can be collected in a separate flask, and will also be left with another flask containing the sodium chloride. Now let's say that we want to separate two volatile chemicals, so we're not so lucky as to be able to have one of them be left behind after one evaporates. And for this example, let's look at two very commonly used organic solvents: ethyl acetate, which has a boiling point of 77 degrees Celsius, and hexane, which has a boiling point of about 69 degrees Celsius. Now if I took a mixture of those compounds and put them inside of a round-bottom flask, I'll indicate the presence of both compounds by showing a series of dark and light circles. If I were to apply heat, and I'm going to show that on this diagram by drawing a heating mantle that would heat the flask up in a very controlled fashion, we would see that the solvent would begin to evaporate. Now, you learned in your general chemistry classes that both of these compounds will not evaporate at the same time, but rather the lower boiling compound will evaporate first, completely before the second volatile or the second compound should evaporate. So if we really want to be able to take advantage of these difference of boiling points in order to separate these compounds, we'll need to make use of a more complicated setup, where instead of just having the round bottom flask and the heating mantle, we'll also want to add on a slightly more complicated apparatus. What you're seeing being drawn right now is known as a distillation apparatus. And in the next video, we'll go through each one of the components one by one, so you understand what each one of them is doing. The key here is that we're adding components that will set the path for the vapors and the liquid, and also a component that will recondense the vapors into a liquid so they can be collected. The idea here is that we would allow for the evaporation process to take place such that the first component would evaporate and recondense, and we would put it in the first flask, and then once that material stopped evaporating and condensing, we would switch the flasks so that the second chemical or second component can be added to a new flask. But how do we know when to switch? Well, one way is to add a thermometer, and we can track the temperature of the inside of the flask as the distillation takes place. So if we look at the volume of liquid that is coming over through the distillation apparatus, and we look at the temperature of that liquid or vapor at that point as it goes through, what we'll see is that with increasing volume, we'll find that the first fraction that comes off will correspond to the 69 degrees, whereas the second fraction will correspond to the 77 degrees. Notice that little dip that I've drawn there. Sometimes you see a little bit of a dip like that in between the two components. And the idea here is that the first fraction would be the hexane and the second fraction would be the ethyl acetate. To review, in this video we looked at several different ways in which chemicals can be separated based on their physical properties. We learned that most commonly boiling point and solubility differences are exploited in order to separate chemicals. And we learned that distillation is a process of separating two volatile chemicals based on their differing boiling points. In the next video, we will look at distillations a little bit more closely, and we'll see what types of factors impact the efficiency of a distillation and the theory that goes behind it.